Hey everybody, Dr. A here, and in this video we're going to be providing some background information on steel beam design using LRFD. So let's go ahead and get started. We need to recall from statics, mechanics of materials, and structural analysis that beams are horizontal flexure members that primarily support internal bending moments M and internal shear forces V. Now, they can also support internal axial loads or normal forces, which we call N. But for the purposes of steel design and really just the overall purposes of the use of beams in general, their primary purpose is to support internal bending moments and internal shear forces. Now, in a steel design setting, we're going to be referencing the AISC Steel Construction Manual chapters F and G, okay? So if you have your steel manual out, you want to go ahead and flip to those chapters. In particular, we're going to start with chapter F, and you might want to tab those up and label them accordingly. So chapter F deals with flexural strength, and G deals with shear strength. So in general, when we deal with steel beam design, there are three limit states, or I should say three collections of limit states that we investigate. The first collection of limit states deals with the flexural strength or the moment strength. The second collection of limit states deals with the shear strength, and then the third limit state is deflection. And again, chapters F and G really dive into flexural strength and shear strength in particular, okay? Now, when we said beams are horizontal flexure members, if I sketch this out, it should be very familiar to you. When we have a beam, a side view of that might look something like this. And, you have different kinds of support systems. Our very common type of beam we see frequently is a simply supported beam supporting some kind of loads. We'll call that maybe W, and maybe there's a P over here. And if we use method of sections, we can make a cut section really anywhere along this length, and we can determine that internal bending moment M or internal shear force V, okay? And so beams and beam systems are very commonly used as roof systems, roof support systems, and bridge deck support systems. So again, the design of steel beams is a very important concept that we need to study, all right? So let's turn the page here, and let's talk a little bit about the high-level aspects of LRFD flexural strength. So load and resistance factor design, flexural strength. So the flexural strength of steel beams is governed by the Steel Construction Manual, Chapter F, all right? And in general, that is governed by this design equation. We need phi b mn to be bigger than or equal to m sub u, okay? Now, what do these terms refer to? Well, phi b is going to be equal to 0.9. This is our flexural resistance factor, okay? And then mn is the nominal flexural strength, and this is going to be based on, put in parentheses here, based on the specific flexural limit state. Remember, we said that Chapter F deals with the flexural limit state, but I also called it a collection of flexural limit states. So it turns out there's several different types of flexural limit states that we need to investigate in a steel beam design setting, okay? And then, of course, MU is the LRFD factored required strength, and this is based on load combos. Okay, so I'll put it in parentheses here from the LRFD load combos. All right, and then that's That's the required moment strength. Obviously, we're talking about moments right here, okay? So when we say nominal flexural strength, that's the nominal flexural or moment strength, okay? And then MU is the LRFD factored required moment strength. So we're dealing with moments here, and that hopefully is obvious with the designation M, okay? Now, what about this next bullet point I have here? Based on theory from mechanics of materials, okay? So some of the theory that we learned back in Mech of Materials or even in structural analysis, that is the foundation of this chapter F, all right? And so let's recall some important things from Mech of Materials. We may remember from Mech of Materials that we had flexural stress or bending stress, sigma B, right? This was called flexural stress. And what was that equal to when we kind of dig out our Mech of Materials toolbox? Well, that was a moment times a centroidal location divided by a moment of inertia, an my over I. And typically, we had flexural strength max was plus and minus MC over I, where C was the largest distance from a compression or tension fiber to the neutral axis. All right, so if we recall again some knowledge from Mech of Materials, if we have a beam here and we have maybe a moment here M, then we would have this flexural stress distribution. You have a compression zone and you have a tension zone, and you had a neutral axis here, and so this was an my, or I should say MC over I compression zone, and then down here was an MC over I tension zone, and this was a linear stress distribution. So these vary linearly as you go away from the neutral axis. So if you're a little rusty on that, I have some videos in my Mechanics of Materials playlist where we dig into the Mech of Materials theory of this, okay? But this is just a quick recap of it. Now, you may remember also from Mech of Materials, we used a section property called section modulus. So S was called the section modulus, okay? And we sometimes called this the elastic section modulus, okay? Now, we could say S sub X for bending about the X axis, the X centroidal axis. This is going to be I sub X over Y bar. And we also had an S sub Y for bending about the centroidal Y axis, and that was equal to I sub Y over X bar, okay? And again, I have some review videos of this. I think this review video or comprehensive background video is in my statics playlist. But regardless, this was a section modulus, and section modulus had units of length cubed, okay? So if you remember section modulus, the concept of that is the first area moment. So it's like you're taking, the way it's derived is you take an area and you multiply it by a perpendicular distance, because you're effectively revolving that area around an axis. So it had units of length cubed, okay? And so if you think of this in terms of section modulus as I over Y bar, and Y bar represents C right here, then how can you rewrite this? Well, you can rewrite bending stress as M over S, okay? And whether it's SX or SY depends on the axis that you're bending about, that you're flexing about, okay? Now, another important aspect that I'm going to give you the overview, a brief overview of it here, and then I'm going to have a whole nother video on it, is the plastic section modulus, okay? So we're going to make another point here, and we're going to say this theory is also based on plastic section modulus theory, okay? Now, Z is called the plastic section modulus, okay? And this has units, so we'll say Z has units also of length cubed. Now, plastic section modulus is something that we, depending on, your mech of materials and your structural analysis background, you may or may not have covered that so far. So I'm going to have a whole nother video after this one where we discuss and kind of derive some background information on this thing called the plastic section modulus. All right. And so for shapes, both S and Z are in table 1-1 of the Steel Construction Manual, okay? So when you have a standard hot rolled shape, and we use W shapes quite often for beams in steel beam design. The great thing is this section modulus and plastic section modulus, the elastic and the plastic section moduli are found in that table 1-1 that hopefully you're already familiar with from your knowledge of steel design. And so you don't have to calculate these from scratch very often. You might have to calculate them from scratch if you have a built-up section, of course, but for the standard hot roll shapes, you don't. They're in that table 1-1, okay? So that concludes this video on basic background information. Again, this is a high-level overview of beam design, and we're going to have some other videos after this where we dig into the more specifics of steel beam design. So thanks for watching, and if you found this helpful, please hit like and subscribe.